The moon is getting its own time standard. That sounds like a joke, until you realize the moon does not keep time like Earth. A clock on the lunar surface ticks slightly faster than a clock on Earth. The difference is tiny for a person, but huge for machines. NASA is working on Coordinated Lunar Time. The deadline target is the end of 2026. This is not about choosing breakfast time for astronauts. It is about navigation, safety, communications, and control. If we build a lunar economy, every spacecraft has to agree on what now means. Without that agreement, the moon becomes a place where clocks slowly drift apart. And when clocks drift in space, positions drift too. That is where a microsecond can turn into a mission problem. The strangest part is that Einstein is hiding inside the schedule. Gravity changes time, motion changes time, and the moon is different enough from Earth that the difference must be measured. So, before humanity builds bases on the moon, it has to build a clock for the moon. This is the story of lunar time. First, this is not really a normal time zone. A time zone is what cities use to organize daily life. Coordinated lunar time is closer to a time scale. It must define how seconds are counted for systems on and around the moon. That makes it more like UTC for the lunar environment. But it has to respect lunar physics. A 24-hour Earth day is not the same thing as a lunar day. The moon takes about 29.5 Earth days to cycle through day and night. That long sunlight cycle matters for power and operations. But the clock problem is even more precise. Atomic clocks on the moon would not match Earth clocks perfectly. They would drift because the moon has weaker gravity. They would also be affected by motion and orbit geometry. For astronauts, that drift feels invisible. For autonomous landers, rovers, and satellites, it is not invisible. Every navigation solution depends on timing. Every signal has a travel time. Every network needs synchronized timestamps. So the question is not what hour lunch begins. The question is, what reference time the entire lunar system trusts? On Earth, we already live inside a timekeeping machine. Atomic clocks define the second with extreme precision. GPS satellites need relativity corrections every day. Their clocks do not tick exactly like clocks on the ground. If engineers ignored that, GPS positions would quickly become wrong. The moon creates a similar problem on a new stage. NIST analysis says lunar surface clocks tick about 56 microseconds faster per Earth day. Some public summaries use about 58.7 microseconds per day. Either way, the number is small but operationally real. A microsecond is 1/millionth of a second. Light travels about 300 meters in 1 microsecond. So 56 microseconds is already many kilometers of light travel. That does not mean a rover instantly gets lost by that amount, but it shows why timing precision matters. Space navigation turns time into distance. Small timing errors become position uncertainty. Position uncertainty becomes risk, and risk is exactly what lunar missions try to remove. The moon is not just farther away. It runs on a slightly different rhythm. So why does this matter now? Because the moon is about to get crowded. Artemis is designed to return astronauts to the lunar environment. Commercial landers are delivering science payloads. Future missions plan rovers, relays, habitats, and power systems. International partners are building pieces of the lunar infrastructure. Private companies want communications and navigation services. China is also building toward long-term lunar operations. A single lander can borrow Earth time and survive. A busy lunar region cannot. Imagine multiple landers descending near the South Pole. Imagine rovers crossing shadowed terrain. Imagine orbiters relaying signals over the horizon. Imagine astronauts coordinating with robots they cannot directly see. All of that requires shared time. Not approximate time, precise time. The moon is changing from destination to workplace, and workplaces need clocks, even when the workplace is another world. Navigation is the first reason lunar time matters. On Earth, GPS works because satellites carry synchronized atomic clocks. Your phone measures how long signals took to arrive. From those times, it calculates position. The moon needs its own version of that logic. NASA's LunaNet concept connects communications, navigation, and networking around the moon. A rover near the South Pole may not see Earth directly, A relay satellite may have to pass the signal. A lander may need to know exactly where it is during descent. A rescue rover may need to find astronauts in shadow. Every one of those actions depends on time. If the network timestamps disagree, the map becomes less trustworthy. If the map is less trustworthy, motion becomes more dangerous. The lunar South Pole is full of extreme light and darkness. Shadows can hide craters. Low sun angles can confuse cameras. Dust can hide landmarks. Precision navigation is not a luxury there. It is the difference between exploration and guessing. Communications are the second reason. Spacecraft do not simply talk like people on phones. They send commands, telemetry, video, science data, and safety messages. Those messages need timestamps. A timestamp tells teams when data was created. It helps engineers reconstruct what happened during a maneuver. It helps autonomous systems decide which information is newest. It helps secure data transfers. If one spacecraft says now and another says now differently, confusion grows. At the moon, signals already have travel time. Earth is about 1.3 light seconds away. That delay is manageable, but it cannot be ignored. Add multiple satellites, orbiters, landers, and rovers, and timing becomes a network problem. A lunar time standard gives the network a common heartbeat. It lets machines agree on sequence. It lets mission control understand cause and effect. And it gives future lunar infrastructure a shared language. Not spoken language, time language. Human operations add another layer. Astronaut schedules depend on power, temperature, lighting, and communication windows. The lunar South Pole has strange lighting conditions. Some ridges can receive long periods of sunlight. Nearby crater floors can remain in permanent darkness. A crew may operate in a world where day and night do not feel familiar. They will need schedules based on mission needs, not sunrise and sunset. They will need local operations time. They will need Earth coordination time. And they will need machine time for navigation and data. Those layers cannot fight each other. A habitat clock, suit clock, rover clock, and relay clock must agree where it matters. Otherwise, small mistakes stack up. A battery swap could be late. A rover handoff could happen at the wrong moment. A communications window could be missed. A science sample could lose context. The moon is quiet in pictures, but operationally, it will be busy. Coordinated time is how busy systems stay calm. Building lunar time is not as simple as placing one clock on the moon. Engineers have to define a reference frame. They have to decide how lunar surface clocks relate to lunar orbit clocks. They have to decide how lunar time connects to Earth UTC. They have to model gravity, motion, altitude, and location. A clock on a mountain behaves differently than a clock at sea level on Earth. The moon has the same kind of problem in its own way. A clock on the surface is not identical to a clock in orbit. A clock near the moon is not identical to a clock on Earth. The system has to be practical for missions. It has to be precise enough for navigation. It has to work with international partners. It has to support old missions and future missions. It has to survive outages. It has to be distributed. And eventually, it may need physical lunar clocks as part of the network. That is why NASA, NIST, international standards groups, and partners matter. This is physics becoming policy, then policy becoming engineering, then engineering becoming infrastructure. The stakes are bigger than one agency. Who defines time also helps define how operations are coordinated. If many countries and companies operate on the moon, they need common standards. Standards prevent chaos. They make docking safer. They make navigation services compatible. They make science data easier to compare. They make rescue operations faster. They also shape power. The first systems often become the systems everyone else must use. That is why timekeeping is strategic. It sounds neutral, but it sets the rules of the road. Earth learned this with navigation, communications, and the internet. The moon may repeat that pattern. A lunar clock is not just a clock. It is part of the operating system for cislunar space. Whoever helps build that operating system gains influence. That does not make lunar time sinister. It makes it important, and it explains why the deadline matters. There are also misconceptions. This does not mean astronauts will wear watches set to one weird moon hour. It does not mean lunar days suddenly become 24 hours. It does not mean people on the moon will abandon Earth time completely. Human schedules may still use familiar formats. Mission control may still coordinate with Earth-based teams. The deeper issue is machine synchronization. Coordinated lunar time is about a shared reference. It helps spacecraft know when something happened. It helps networks route signals. It helps navigation systems solve position. It helps missions compare data across platforms. Think of it like the invisible grid behind the visible mission. The public sees astronauts. The machines need timestamps. The public sees rockets. The networks need clock discipline. The public sees a moon base. The base needs a time architecture. That architecture is being built before the base is fully real. Imagine a rover driving near a shadowed crater. It receives a navigation update from an orbiter. The orbiter received data from another relay. Mission control sent a command from Earth. Each step depends on time. If the timing chain is uncertain, the rover's position is uncertain. If the position is uncertain, the route becomes risky. If the route is risky, the mission slows down. Now imagine a lander descending in dust. It needs radar, optical navigation, engine timing, and communication links. A small timing mismatch can become a bigger guidance problem. This is why space engineers obsess over clocks. They are not being dramatic. They are preventing invisible errors from becoming visible failures. The moon will not forgive sloppy timing. It has no GPS constellation yet. It has no cell towers. It has no repair truck. So, the clock has to be part of the safety system. Before the first true lunar neighborhood exists, its timekeeping must already work. The moon is only the beginning. If lunar time works, Mars will need its own system too. Mars clocks differ from Earth clocks even more. Mars also has a different day length. Future crews on Mars will need local time, Earth coordination, and machine timing. Deep space missions will need standards that scale beyond one planet. That is why NASA talks about celestial time standardization. A moon clock is a first step toward a solar system clock architecture. It sounds abstract now, but so did GPS before it became normal. So did internet time before every device depended on it. Infrastructure feels boring until it disappears. Then everyone notices. Lunar time may become invisible if it succeeds. Astronauts will simply navigate. Rovers will simply sync. Landers will simply coordinate. And the public may forget how strange the problem once sounded. That is what good infrastructure does. It makes impossible coordination feel ordinary. So the moon getting its own time standard is not a gimmick. It is a sign that exploration is becoming infrastructure. Apollo could use mission time because Apollo was a visit. Artemis needs coordinated time because Artemis is trying to stay. A visit can improvise. A settlement needs systems. A rover needs navigation. A lander needs synchronization. A habitat needs schedules. A relay network needs timestamps. And astronauts need machines that agree with each other. The moon is becoming a place with traffic, data, power, and operations. That means it also needs a heartbeat. Coordinated lunar time is that heartbeat. It will be measured in tiny differences, microseconds per day. But those microseconds are the beginning of something much larger. A moon that can be navigated, a moon that can be worked on, and eventually, a moon that can become the first clock in humanity's road to Mars.